All right. We are looking at free energy and equilibrium. We have talked about free energy. That means Gibbs free energy, the energy that's not tied up in any form of entropy. It's free to do work. We've talked about that the past couple days. And we talked about equilibrium, and this is the unit 7 equilibrium, so not as bad as buffer equilibrium. Okay, so just straight up like what the concept of equilibrium is. We know that when we are dealing with K values, so I'm taking you back to unit 7, K values that are larger than 1 show that the products are favored at equilibrium. K values that are less than 1 show that the reactants are favored. If we apply the same idea to Gibbs free energy, we know that reactions with a negative delta G are thermodynamically favorable, meaning the products are favorable. Therefore, K values greater than 1 are thermodynamically favorable. So K values greater than 1 favoring the reactants will be thermodynamically favorable. If you have a negative delta G, then you're going to have a K value greater than 1. So that's what they're saying here. Negative delta G, K is greater than 1, your products are favored. Okay. Now, we are going to introduce you to your third to last equation of the year. Yay. Yay, indeed. Okay. So this is a Gibbs free energy is equal to negative RT natural log of K. A lot of times we call this rat link. Can you see the word rat and link? Okay. So if you hear us refer to rat link, that's what we're talking about because it kind of looks like rat link. And this R value here is going to be equal to this R value on your sheet. Here, come here for a second. Come here. See the pink shirt right here? Can you give that to her? Thank you, honey. Appreciate your helping me. All right. So you have several different R values listed here. These are your gas constants. Okay. This one is the only one that has joules in it. So that's the one you're going to use. Okay. Additionally, this is pi, right? 3.14. And rats eat pie. Whatever you got to do to help you remember. The logical way or the crazy way, as long as you remember, it's fine. Okay. Now, this equation is on your equation sheet. This one is not. Not on your equation sheet. They are the same things. This one has a natural log in it of K. To get rid of a natural log, you do E to the whatever it is. Yes? Okay. So they're just showing you how to rearrange this to solve for K. The one thing that I typically have issues with on this is I will forget that negative sign right there. But if you remember that cats or rats are bad, they're negative, that'll help you out. It all comes back to rat. All right. Now, here, when delta G is near 0, K will be near 1. As delta G becomes more negative, K is going to get bigger because it's going to be favored more. If G becomes larger, more positive, then K is going to get small. So down here, there is this 10 to the 6 should have been up here. It got kind of orphaned down here, so sorry about that. If we look at this value of K, what sign is your delta G going to be when we solve? Negative. Is this a big number? Then your delta G is going to be a big number, a big negative number. So it's good to go back and kind of check your work and see what you're getting. Okay, now we're going to substitute and solve. So I had delta G. Have you been keeping up with the videos at all?
I have another packet.
Okay. So delta G is going to be equal to my R. And again, I have to use this one times my temperature, which is 298. And we know that it's going to be 298 because this prime is here. And that tells us that we're at standard conditions. Standard conditions have our temperature at 298. Then we are going to multiply that by the natural log of K. So 1.40 times 10 to the 6th. And again, I always forget my negative at the beginning. Bad lippy. Gonna equal. All right, so let's see what that comes out to be. And that's going to be a negative, and that's going to be kilojoules per mole. Did it come out to be negative?
Yeah.
Okay, so that's correct. Did it come out to be a really big number?
Yeah.
So that is correct. Everybody happy?
Did you just round up?
Yeah. All right, good. You do this one. Go. All right, how did you do? You need more time. All right. So this is going to be homework for this one. And now I'm going to move on to 9. I think it's 9.6. All right. Anybody need this one up still? Okay. So I'm going to move on to 9.6. Now, 9.6 is kind of an orphan. It doesn't really belong here, and it doesn't really belong there. They used to have it in Unit 7. That was 7.14, I think, is what it was titled. This year, they moved it into this unit in this section and made it 9.6. So if I don't have a chance to redo some of my answer keys, everything after this is going to be a one number less. So your 9.7 was last year's 9.6. Your 9.8 is last year's 9.7. And then this answer key will be over in Unit 7's answer keys. And I'm going to try to get something uploaded by the end of the day that is good for the rest of the... Do you follow me? Am I making any sense at all? Okay. All right. But this guy is kind of an orphan. They don't know really where to put him, but he did not make any sense in Unit 7. I can give you that, because in Unit 7, you don't know anything about entropy. So here we were talking to people about entropy, and we hadn't introduced it. There was no introduction to it prior to this. Nobody knew what was going on. So now they've moved it over here, so it makes a little bit more sense, I think. But now all my answer keys are off just a little bit. All right. There are two driving forces that determine the spontaneity or whether a reaction is thermodynamically favorable, because we don't like the word spontaneous. Okay. Spontaneous is saying if it is a reaction will happen, not how long it takes. That's why they like you to use thermodynamically favorable. The first driving force is enthalpy. Enthalpy, then, what we know about that is that exothermic reactions are favored. Okay? So when we talk about dissolution reactions, we're talking about something dissolving. So you've got sodium chloride, you throw it in water, it's going to break out into sodium and chlorine. Okay? We learned yesterday that in terms of entropy, that positive entropy is favored. In other words, the universe is going towards more microstates, or some people think of that as disorder. Okay? So that is our entropy. If we have a container at standard temperature and the particles are moving within the container, they have kinetic energy, of course. If the solution's heated, they're going to be moving faster, right? Higher velocity. So they're going to have a higher entropy. Also, mixing two substances together is going to increase the entropy. It will increase it because we've increased the volume. You increase volume, you have more microstates, more places for that stuff to go. So our entropy increases as well. And they are generally, so this means solution formation is usually something favorable. Entropy favors it. I can't pronounce that. All right. Again, delta S, delta H are linked by Gibbs free energy. Several ways to kind of calculate that. We talked about one yesterday. We talked about another one today. And we'll talk about, I believe, a third one coming up within the next day or so. Yeah, we got one more to go with that one. All right. We are to the point now where we have 3 formulas left to cover. All right. So when we look at something breaking apart, we have to input energy to get water to break apart. Okay, think about magnets. If you had 2 magnets stuck together, you'd have to input energy to pull them apart. Yes? So that's why the delta H is positive. When you pull things apart, they become less ordered, right? So that gives you a positive delta S. We're doing the same thing here for the solute. But then when they come back together, that is exothermic. It's going to release energy. So when you have 2 magnets that come together, they're going to release energy. They might make a sound. Sound is energy. Do you know that? Sound is energy. You know? Sound is energy. It might, it has some force that it's going to click together with. So that is going to release energy. And then this is going to make it more ordered. The system becomes more ordered because you're starting to form things around the material. So that makes it more ordered. Less places that it can be because it has to be locked in to one of these other things. And I'll show you a picture here in just a second. All right. So our first question here, solution, which one's going to have greater entropy? So we have one here with a KSP at 10 to the negative 15 and one at 10 to the negative 22. Which one's going to have more entropy? Huh? A, why? More of it reacts. More of it, this is a saturated solution, more of it is going to be in solution, broken out into its ion form. And more of this will stay in its solid form because this value is smaller than this one. So A is the correct answer there. All right, I got water molecules drawn here. What are these dashed lines representing? Huh? Intermolecular IMFs, yep. Okay. So we have to break those. We have to input energy to break those IMFs so that when we come over here, they can surround material in the aqueous form. Okay, so I got my water placed over here. All right, now I'm going to draw this. Okay, what's connecting these things? Huh? Ionic bonds, yes. So we have to pull those things apart. That's going to require some energy. When I pull that apart, which one of these is going to be in this section right here? Chlorine. Why? These are my positive ends of my water. They're going to be attracted to the chlorine. Do you see how this looks more ordered than just all of these things without, if they were free-flowing without these forces holding them together, these are going to be more ordered. And then that would be the calcium over here. It's attracted to the negative end of the water molecule. What are the forces here? What are those called? What's this thing called? That's an ion. And then the force between them is going to be what? It's ion dipole force, which is an intermolecular force, an IMF. Okay, that's what's holding those water molecules in place there. Good? Any questions on that orphan unit? All right, moving on. Nope, we're not ready for coupled reactions. Did I get through everything already? Maybe I did. Oh, that is it. Yeah, we'll do